Hi, my name is John Mark M. Cubacub, and I will present the activity in calculus. The topic is work problem featuring calculus. The first problem is a variable force or in Newton acting on an object is represented by the function of f of x is equal to x squared minus 2x plus 5, where x is the distance in meter from the origin. How much is required to move the object from x is equals to 1 to x is equals to 4? The work done by a variable force is the definite integral from a to b of the force function times dx. So in this case, a is 1, b is 4, based on the values that we see here. F of x is equals to x squared minus 2x plus 5. The antiderivative of x squared is x cubed divided by 3, and the antiderivative of 2x is 2x squared over 2, and the antiderivative of 5 is 5x. So let's evaluate it from 1 to 4. So if we plug in 4, it's going to be 4 cubed over 3, and then 2 times 4 squared over 2 plus 5 times 4, and then we, we need to plug in 1, so it's going to be 1 cubed over 3 and minus 2 times 1 squared over 2 plus 5 times 1. Now 4 cubed over 3 is 64 over 3, and 2 times 4 squared over 2 is 16, plus 5 times 4 is 20. And on the right, we have 1 over 3 minus 2 times 1 squared over 2 is 2 minus 5. So this is 64 over 3 minus 16 plus 20. If we distribute the negative sign, it's gonna be negative 1 3 1 over 3 plus 2 minus 5. So now let's continue, like let's combine like terms. So we can combine this to 64 64 over 3 minus 1 third is 63 over 3, minus 16 plus 20 is 4, and plus positive 2 minus 5 is 3, is negative 3. 63 divided by 3 is 21, and 4 minus 3 is equals to 1. So 21 plus 1 is equals to 22 joules. Problem number 2. A force of 20 pounds is required to hold a spring stretched 5 inches beyond its natural length. How much work is required to stretch it from its length to 10 inches beyond its natural length in feet-pounds? So let's talk about spring. So this is spring that is in natural state. In order to stretch a spring, you need to exert a force, and in order to hold it in this position, you have to apply a certain force. The spring must slap back, and so there's a restoring force that wishes to pull it back. So to calculate the force that's required to hold it at the new position, that force is equal to the spring constant times x, where x is the distance between its natural length and its current length. Now k is constant, and k can be found by taking the force divided by x. So in this problem, we need to find k. 20 pounds of force is required to stretch the spring 5 inches beyond its natural length. So x is 5 and 20 divided by 5 is 4. So k is 4 pounds over inch. So so that we have k, we can write the force as a function of x, so it's gonna be k times x or 4x. So that's the force required to stretch the spring at any distance x from its natural length. So now we can calculate the work. The work done is gonna be the definite integral of f of x times dx. So we want to calculate the work required to stretch it from its natural length. That's when x is 0 to, to 10 inches beyond its natural length, which is x is 10. X is the distance from the natural length to current position. So the work is gonna be the integral from 0 to 10 f of x, which is 4x times dx. The antiderivative of 4x is 4x squared over 2. So 4 divided by 2 is 2. So it's gonna be 2x squared evaluated from 0 to 10, and that's 2 times 10 squared minus 5 times 0 is equals to 2 times 100, and that and the unit are pound pound times inches. Now we wanted to convert it to pounds times feet. So 1 foot is equals to 12 inches. So the unit inches the unit so the unit inches will cancel, and so that become 200 over 12 feet pounds. Reduce it, 200 over 12 is equal to 16.6 feet pounds, and that's it. Problem number 3. How much work is required to lift a 200 pounds crate up a distance of 100 feet using a rope that weighs 4 pounds per feet? So there's two parts. The first part is we need to lift up the crate. So how much work is required to lift up a box or a crate? The work required is simply force times distance, and so the force is the weight of the crate, which is 200 pounds, and we live in and off by a distance of 100 feet. So it's gonna be 200 times 100, and that is 20,000 pounds times feet. So that's the work required, but just to lift the crate. Now we need to calculate the work required to lift off the rope by a distance of 100 feet. So first we need to write an equation. The force that required to lift up the rope in terms of x, and it's gonna be the weight density in pounds per feet times the distance that we're lifting it up. So the first equation is to be 4 pounds per feet times x, or simply 4x. So the work required is give me the definite integral from a to b. So from 0 to 200, we're gonna integrate 4x times dx. So 4 divided by 2 is 2. So we have 2x squared. So that's gonna be 2 times 0 squared minus 0 squared is 200 squared is for 200 squared is 40,000. If we multiply it by 2, that's gonna be 80,000 pounds times feet. So the total work required to lift up the crate along with the rope is gonna be the sum of the 80,000 plus 20,000 is 100,000 pounds times feet. So that's the total work required to lift up the crate and the rope. Problem number 4. Find the work done in pushing a car in a distance of 10 meter with a constant force of 500 Newton. The formula is work is equals to force times distance. Work is equals to the force is 500 Newton times the distance, which is 10 meter, is equals to 5,000 joules. Last problem. Find the work done in pushing a cart in a distance of 20 meter with a constant force of 300 Newton. The formula is work is equals to force times distance. Work is equals to the the force is 300 Newton times the 20 meter, which is the distance. Work is equals to 6,000 joules. Thank you for listening.